Imagine being able to track and visualize game data in real time, right in your UI, whether it's enemy positions, resource flows, environmental changes, or even simulating fluid dynamics and procedurally generating terrain, all powered by a compute shader. Today, we're going to create a custom scriptable render feature in Unity 6 so that we can efficiently generate dynamic heat maps, all running on the GPU for lightning-fast performance, enabling interactive real-time visualizations like this directly in your game's UI or even in your world. Let's get into it. Let's start by writing our render feature class. Our class is going to inherit from Scriptable Render Feature, which has two required methods. The first method we're going to overwrite is create. This is called when the render feature is created by Unity. The second is to add render passes. This gets called once per frame per camera and injects our scriptable render pass instances into the renderer. A render pass is a unit of GPU work that performs a specific stage of rendering, such as drawing objects or running a compute shader or compositing within a frame's render pipeline. Finally, and optionally, we can override the dispose method, and here we can do any kind of cleanup we want to handle. So these three methods make up the basic building blocks of a scriptable render feature. And I'm just going to collapse them down to definitions only so that we have a little bit more room to write the actual render pass itself. This inner class will define the specific logic that will run during our injected render pass. Now, before we define our scriptable render pass, I'm going to need a few more using statements. Let's pull in Unity Engine. Unity Engine.rendering, so we have access to render textures and their handles, the render graph module so that we can access the render graph, and experimental.rendering because I want to use a specific type of graphics format. We'll see all of these things in just a minute. Now we can start setting up our scriptable render pass. It's going to need a few references. First of all, I want to keep a reference to the compute shader that we were going to actually use in our processing. We're also going to keep a reference to the kernel. The kernel is the entry point function in our compute shader that defines the code that's going to be executed by each thread on the GPU. The integer represents the index of that kernel function. Because we're building a heat map of enemy positions, I'm going to use a GPU buffer to hold all the positions, and we're going to pass this buffer into our compute shader. We're also going to need a CPU side array that we'll use to populate the buffer each frame. Now, in today's example, we're going to simulate 64 different enemies on the map. So we're going to need to allocate enough buffer space to handle that. If you had more, of course, you would allocate a little bit more. And it's a good practice to increase this in powers of 2. So 64, 128, 256, and so on. Next, let's define an RT handle that will be a wrapper for our heat map texture. An RT handle is a wrapper that will hold a reference to the texture and some other metadata like scaling factors and viewport size and other things like that. I already know the size of the texture I'm looking for, so we can initialize some variables for that as well. Finally, I'm also going to expose that RT handle with a public property so that we can reach in here and get a reference to it if we need to. And that's all the fields we need for this inner class. I'm going to wrap these up in a region and then just collapse it so that we have a little bit more room to work with. Now let's get started by writing a setup method. This will take in the compute shader and we can set that into our compute shader field. We can also get the index of our kernel just by looking it up by name. For some other setup, if the heat map texture doesn't exist or has changed dimensions, let's reallocate for that. First of all, let's clean up any old handle if there is one. Now we can assign a new descriptor. Here we can set the width and height, the graphics format, which here I'm saying each texel will store a single 32-bit floating point value, with each texel representing an amount of heat on our map. The last 0 means there's no depth buffer attached. Then for properties, we can enable random write, which enables unordered access inside of compute shaders. The MSAA sample set to 1 disables multi-sample anti-aliasing. Since this is a compute shader, MSAA is unnecessary. We'll disable sRGB gamma correction because we're going to use the linear color space. If we were to set this to true, that would apply a gamma curve on read-write. Finally, let's disable MIP mapping. MIP mapping isn't useful here because we're not sampling this texture with varying levels of detail. Now with our descriptor, we can allocate the GPU texture using the RT handle system. So this takes care of our heat map handle, but we should also allocate our enemy buffer. So let's do something similar to what we did with the handle. Let's see if we need to allocate or resize the enemy buffer and the CPU array. We can free up GPU memory if the buffer does exist. Then we can assign a new structured GPU buffer that can hold a list of float2 values, one for each enemy's position, by allocating enemy count entries, each one the size of 2 floats, one for X and one for Y. Similarly, for our vector2 array, let's make it exactly the same size, enemy count. And that's all the setup we have to do. So let's collapse this up so we have a little bit more room. And now we can move on to defining a data structure that we're going to pass into the render graph pass function. I'm just going to call this pass data. This data is going to contain references to our compute shader, the kernel index, our texture handle output, a buffer handle that'll be a GPU side handle to enemy positions, and the enemy count. So this container groups together all the parameters and resource handles that the render graph needs to bind when executing the compute shader. So let's collapse this up and we're going to put it to work. The next method that we're going to write is the actual render graph pass, which is called every frame. And this method is called record render graph. Now, normally I would pass in an array full of real enemy positions, but for this example, we're going to fill it up with random positions. Let's loop over each enemy from index 0 up to enemy count so we can assign a simulated position to each one. We'll create a time-based value t that changes every frame, offset slightly per enemy so they don't move identically. For the x position, we can sample Perlin noise using time and the enemy index, then scale it by the texture width so it maps to the heat map space. Same idea for y position, but we flip the order of inputs to get a different noise pattern and scale it by the height. Finally, we can store the generated position as a vector2 into the array at index I. Now, the values 1.31 and 0.91 are arbitrary prime-ish multipliers that we can use to create more interesting and varied noise input patterns across the enemies. Now we can take our vector2 array and upload this data into the GPU buffer. Then we can import our heat map texture into the render graph so it knows this texture is involved in the graph's dependency chain. Same for enemy positions. We import the structured buffer into the graph so it can be read in our compute pass. We can use the iCompute Render Graph Builder interface. This gives us a builder that will configure a compute pass for Unity's render graph system. This is where we're going to take advantage of that pass data structure that we created before. We can populate that class by assigning the compute shader itself, the kernel index, the output texture, the enemy position buffer, along with how many enemies to process. Then we can tell the render graph that this pass writes to the texture so it can schedule passes in the right order and manage memory efficiently. Same idea for the enemy buffer. We mark it as read-only in this pass. Now we define the actual code that will run on the GPU. This lambda gets executed later when the frame is being rendered. We can send the number of enemies into the shader as an integer. Then we can bind the enemy position buffer so the shader can access it. Same for the output texture. This is where the compute shader will write its results. Finally, we launch the compute shader. We're dividing the texture into 8x8 thread groups so that every pixel is covered in parallel. Now we're almost finished writing our render pass and its parent render feature. Just a few more things to do. I'm going to add another method here that I'm just going to call cleanup. This is so I have a cleanup method I can call from the parent class just to make sure we don't have any dangling references or memory leaks. If there's a heat map handle, let's release it and set it to null. If there's an enemy buffer, release it and set it to null. Okay, now let's move away from the inner render pass class and finish up the parent. The parent is what's going to be accessible to us from Unity. So here let's have a serialized field where we can actually drag and drop in our compute shader. We'll also keep a reference to our heatmap pass object. And so that I can reference this render feature from any other code in my game, I'm going to create a public static reference to this instance. Now before we had an empty create method. Let's fill that out. Let's instantiate our custom render pass and specify when it should be run. In this case, before rendering any objects. Then we can also store a static reference to the feature so that the other scripts can access it. Now let's come down to the bottom and fill out our dispose method. Here, there's not much to do. I just want to call the cleanup method that we wrote earlier from our pass. If we come up to the add render passes method, here's where we're going to inject our render pass into the execution pipeline. Let's do a quick safety check. If compute shaders aren't supported or the shader hasn't been assigned, we skip the pass. Otherwise, we configure the render pass by passing it the compute shader for use for this frame. Finally, we enqueue the pass so Unity knows to run it as part of this frame's rendering. Now, one last thing, let's create a utility method so that other systems can retrieve this heat map texture whenever they want it. And there we go. We have a complete render feature for Unity 6. But there's still a few things left to do before we can try it out. One of them is we have to actually write a compute shader. Let's go through this step by step. First, we have a pragma declaration that's saying that CS_main is the entry point for the compute shader. This is the function the GPU will call when we dispatch the shader from C#. Now, the function is the entry point for our compute shader. The parameter coming in gives each GPU thread its global position in the dispatch grid, which we use to determine which pixel this thread is responsible for computing. We can tell the GPU to execute this shader in thread groups of 8 by 8 threads, so 64 threads run in parallel per group. The compute shader is going to need a little bit more information. Let's have a reference to our output texture. So each pixel will hold a single float value representing the heat at that location. And we can have a float too that will hold the width and height of the texture. We can have a reference to the structured buffer that's holding the 2D positions of all the enemies. And of course, we can also keep track of the enemy count. Now for the shader itself, let's store the thread position as an integer 2D coordinate. This maps directly to a pixel in the heat map. We copy the pixel coordinates into a float 2. This will let us use it in distance calculations without casting. Let's initialize a local variable to accumulate the heat contributed by each enemy. Then we can loop over all the enemies and calculate how much each one contributes to the current pixel. We'll read the position of the current enemy from the buffer, measure how far this pixel is from the enemy's position. Then we can define the influence radius. Enemies beyond this distance contribute nothing. We'll apply a linear fall off so that full heat will be at the center, falling to 0 at the edge of the radius. We can clamp it with saturate to keep it between 1 and 0. Now, after accumulating all the enemies, we clamp the final heat value to 1. This avoids overflowing when multiple enemies overlap. Finally, we write the computed heat value to the corresponding pixel in the output texture. And that's it. That's our compute shader that creates a heat map texture for us. One last little bit of code. I'm going to make a visualizer class that will apply that texture to a material for us so we can see it inside the game. Let's have a reference to that material. Then in every frame update, let's get a reference to our render feature. If for some reason we can't do that, let's just bail out. Then we can get our heat map texture from the render feature. And as long as that's not null, let's just assign that texture to our material. All right, now let's get over to Unity and put this all together. So I've added a quad to my scene here. There's nothing special about it except that I've disabled the mesh collider. If we come up to project settings and go into the graphics setting, you'll find a quick link to your render pipeline asset. If you click that, it'll ping the asset in your project, and right beside that, you should find the renderer. This is where we're going to add our render feature. You can click Add Render Feature and choose our new heat map render feature from the list. Then in your project, go to where you saved your compute shader and drag it here into the field. Now, if I come back to the quad I created earlier, I can also drag onto this, my new script for the visualizer. Here, it expects us to have some kind of material. I've just created a really simple material here that is type unlit texture because we want to, of course, show a texture here. It doesn't have to be anything fancy. I'll drag that material into the slot, and that's all we have to do. Except hit play, of course, so that we can test it out. And there we go. We have some real-time simulated data showing here on the quad. We could probably get a better view of this from scene view. It looks not bad. You can see the fall off happening around each of the enemies. Now, obviously, you don't have to display your computed values onto a texture like this. You can do anything you want with them. So if you're doing procedural generation or you're trying to simulate fluids or whatever, Compute Shader is a great way to do that. Now, of course, we can also display that in the UI if we actually put this onto an image. It works just as well. It just takes a few extra lines of code, which I'll include in the source code for this video. There's nothing too special about it. All you have to do is convert the texture into a sprite. But this is as far as we're going to go with this topic today. If that was your first time ever seeing a render feature or a compute shader, if you're not, we're going to go into more detail on these kinds of topics as we continue with the channel. There's a new video every Sunday, so hit that subscribe button and click the like button while you're there. And of course, don't forget to join us on Discord, where you're going to meet all kinds of other game developers who are more than happy to tell you about their project and talk to you about yours. I'll throw another video up on the screen. Maybe I'll see you there.